Let's start with this problem. A 100 millihenry inductor is in series with a 50 ohm resistor and a 12 volt AC source with a frequency of 60 Hz. What is the inductive reactance in the circuit? So let's draw the circuit. So let's say this is the AC signal, and this is the resistor and the inductor. So we have a 12 volt signal and the frequency is 60 Hz. Now we have a 50 ohm resistor and a 100 millihenry inductor. So let's start by calculating the inductive reactance in a circuit. The inductive reactance tells us how much the inductor opposes an AC signal. It's equal to 2 pi FL, where F is the frequency, L is the inductor. The frequency in this example is 60 Hz. The inductance is 100 millihenries, or 100 times 10 to the minus 3 henries. Milli is 10 to the minus 3, micro is 10 to the minus 6. So the inductive reactance is 37.7 ohms. Now let's move on to part B. Calculate the impedance of the circuit. So the resistance, inductive reactance, and impedance, they all share the same unit. They're all measured in ohms. So they tell us basically the opposition towards an AC signal in the circuit. Now the formula that you need in order to calculate the impedance is this equation. It's equal to the square root of R squared plus XL minus XC squared. Now we saw that XL represents the inductive reactance. XC, on the other hand, represents the capacitive reactance. So we don't have any capacitors in this circuit, so therefore XC is equal to 0. So Z is going to be the square root of R squared, which is 50 squared, plus XL, that's 37.7 ohms. XC is 0. And so this is just the square root of 50 squared plus 37.7 squared. The impedance of the circuit is 62.6 ohms. So that's the answer to part B. Now let's move on to part C. What is the RMS current flowing in the circuit? V is equal to IR. But in this example, V is going to equal the RMS current times the impedance. So the RMS current is going to be the source voltage, or the voltage of the AC signal, divided by the impedance of the circuit. So we have a 12 volt signal and the impedance is 62.6 ohms. So the current that's flowing in this circuit is 0.1917 amps. And so that's the answer for part C. And now let's move on to the next part. Calculate the voltage across the resistor and the inductor. The voltage across the resistor is simply the RMS current times the resistance. V is equal to IR, according to Ohm's law. So the current is 0.1917 and the resistance is 50 ohms. So the voltage across the resistor is 9.585 volts. Now let's do the same for the inductor. The voltage across the inductor is going to be the current multiplied by the inductive reactance. So it's 0.1917 times 37.7 ohms. And so that's going to be 7.227 volts. Now we can confirm our answer. But before we do, notice that the voltage across the resistor and the voltage across the inductor does not add to the voltage of the source. However, there is an equation that will help us to relate the voltage of the source with the voltage of the resistor and the inductor. And it's this equation. The source voltage is going to be the square root of VR squared plus VL squared minus the VC squared. Very similar to the impedance equation. Now VC is 0 because there are no capacitors in the circuit. So in this example, VR is 9.585 and VL, that's 7.227, and then let's square that. And so this will give you 12 volts, which is the voltage across the source. And so that's how you can confirm your answer to make sure that you have the right voltage across the resistor and across the inductor. Now let's move on to the last part. How much power is consumed by the circuit? Now there's two ways in which we can get this answer. First, you need to realize that the power consumed by the circuit is the power absorbed by the resistor. The inductor, it absorbs energy, but then it releases it back. So there's no net gain or net loss with the inductor. It takes, but it gives it back. The resistor only takes energy from the circuit and it doesn't give it back. So the resistor is the one that consumes energy in the circuit. So the power consumed by the circuit is going to equal I squared times R. So that's going to be 0.1917 squared times the resistor, which is 50 ohms. And so the power consumed by the circuit is 1.837 watts. Now there's another way in which you can get the answer. First, let's calculate the power factor. The power factor, which is represented by cosine, it's equal to R divided by Z. So in this example, R is 50 ohms. The impedance, let me see if I remember what that was. That was 62.6 ohms. So the power factor is 0.7987. Now the power consumed by the circuit is the voltage, the source voltage of the circuit, times the RMS current multiplied by the power factor. So VRMS, that's 12 volts in this example. IRMS, that's 0.1917 multiplied by this number, 0.7987. And so this gives you the same answer, 1.837 watts. So those are the two ways in which you can calculate the power consumed by the circuit. You can calculate the power absorbed by the resistor using the formula I squared R, or you could use V times I times the power factor cosine. So let's review some formulas that we went over. So the inductive reactance is 2 pi FL. So if you increase the inductance of the circuit, the inductive reactance will increase. And if the inductive reactance increases, the current in a circuit will decrease. If you increase the frequency of the AC signal, the inductive reactance will increase. And so the current will decrease. So let's say if you have an inductor. In a DC circuit, the current that flows through the inductor will be relatively high. The inductor doesn't really provide much opposition to a DC current or direct current. However, if you have an AC current flowing in the circuit, the inductor has a very high inductive reactance to an AC circuit, especially if the frequency is very high. So an inductor is very useful for passing a DC current or DC signal, but blocking an AC signal. You can also use inductors as filters. And here's two simple ways to use it. So let's say if we're dealing with this circuit. If you have an AC signal with a low frequency, the inductive reactance will be low. So an AC signal with a low frequency can easily pass through the circuit. However, if you have an AC signal with a high frequency, the resistance of the inductor, the inductive reactance rather, is going to be very high. And so an AC signal with a high frequency will prefer to flow this way. But a low frequency signal will easily pass through the inductor. And so this type of circuit could allow low frequency signals to pass through, but filter out high frequency signals. Now, for the circuit on the right, a low frequency signal can easily flow through this inductor. But the high frequency signal, it will be very difficult for it to pass through that inductor because the resistance will be so high. So the high frequency signal will flow through the resistor. So this circuit will allow a high frequency AC signal to pass through, but it will filter out a low frequency signal. And so you can use inductors to either pass high frequency signals and filter out low frequency signals, or vice versa.